A thin film of liquid is creeping silently up the inside of a glass beaker with nothing pushing it. It climbs over the rim, it drips down the outside, and nothing is making it do that. No pump, no heat, no trick. Just a liquid that has decided gravity is someone else's problem. This is helium-4, cooled to just above absolute zero, and it has entered a state of matter unlike anything else in the universe. Scientists call it a superfluid. A liquid with zero viscosity, it flows without any friction at all. But discovering it took decades of obsession, failed experiments, and one very stubborn physicist who refused to quit. The story starts in Leiden, Netherlands, in 1908. A scientist named Heike Kamerlingh-Onnes was chasing the coldest thing ever made. He liquefied helium for the first time in history, reaching just 4 degrees above absolute zero. The world had never been that cold. Onnes noticed something odd almost immediately. Below 2.17 Kelvin, liquid helium changed. It behaved differently. Strangely, the bubbling stopped. The liquid went eerily calm. It was as if something fundamental had switched off inside it. Onnes called this strange phase helium-2, but he couldn't explain it. Nobody could not yet. For nearly 30 years, helium-2 sat unexplained. Then in 1937, a Soviet physicist named Pyotr Kapitsa changed everything. Kapitsa ran a deceptively simple test. He forced liquid helium through an impossibly thin gap, and it flowed through with no resistance whatsoever. He coined the word superfluid, a liquid with zero viscosity, frictionless, unstoppable, unlike anything physics had ever described. But naming it wasn't explaining it. What force, if any, was actually driving that liquid up the wall? The answer, it turned out, wasn't in classical physics at all. It was hiding in the deepest rules of quantum mechanics. And those quantum rules didn't just change how scientists thought about helium, they rewrote what we thought liquid could even be. Helium, at extreme cold, stops behaving like atoms bumping around randomly. Every single atom falls into the exact same quantum state they move, as one. And that shared quantum state changes everything. The liquid stops acting like a crowd and starts acting like a single, perfectly coordinated entity. But to understand how we got here, we have to go back. Back to a frozen laboratory in the Netherlands and one man's obsession with cold. Leiden, 1908. Heike Kamerlingh-Onnes had spent 2 decades building the coldest place on Earth. His laboratory was a fortress against heat. Every gas known to science had already been liquefied. Oxygen, nitrogen, hydrogen. Helium alone refused to yield. It was the last holdout. Helium boils at just 4 degrees above absolute zero. To catch it as a liquid, you had to get colder than anyone had ever gone. Onnes wasn't just a scientist, he was a logistics genius. He had to manufacture his own liquid hydrogen just to pre-cool his apparatus before even attempting helium. The morning of the 10th of July 1908, Onnes and his team started the pumps before dawn. 14 people worked in shifts. The whole city of Leiden knew something was happening. Hour after hour, they pushed the temperature down. Past 20 Kelvin. Past 10. The equipment groaned. Gaskets failed. They fixed them and kept going. Then, at around 6 inches the evening, something changed. Inside a tiny glass vessel, a faint shimmer appeared at the bottom. Liquid helium. They had done it. Liquid helium existed. Onnes reportedly said the sight was almost invisible. The liquid was so transparent it was barely there. Leiden became the center of the low-temperature universe. If you wanted to do serious cold science, you came here. This lab held the only liquid helium on Earth. Liquid helium was rarer than gold and harder to make. Every drop was earned. Every experiment was a negotiation with the cold itself. And Onnes kept pushing lower. He wanted to reach absolute zero itself, the temperature where all atomic motion stops. He never quite got there. Nobody has. But even without reaching zero, the extreme cold was already revealing secrets. Metals conducted electricity without resistance. That was superconductivity discovered right here. Cold was not just the absence of heat. It was a key that unlocked hidden states of matter, states that simply do not exist at normal temperatures. And liquid helium itself still had its biggest secret locked away. Nobody suspected what would happen when you cooled it just a little further past a peculiar temperature called the lambda point. Past the lambda point, 2.17 Kelvin, something extraordinary happens to liquid helium. The moment you cross that threshold, everything changes. In the Leiden lab, technicians first noticed something odd with the boiling. Normal liquids bubble vigorously. When they boil, helium suddenly went dead calm. Boiling requires pockets of vapor forming inside the liquid. Below the lambda point, helium stops doing that entirely. The surface just sits there, eerily smooth. It was unsettling. The equipment was pumping heat out. You could hear the vacuum pumps working, but the liquid just refused to respond like any liquid should. Then came the heat measurements. When researchers tried to measure how helium conducted heat below the lambda point, the numbers came back absurd. Liquid helium below 2.17 K conducts heat hundreds of times better than copper. That is not supposed to be physically possible for a liquid. Normally, heat moves through a liquid sluggishly, molecule bumping into molecule. But helium below the lambda point was moving heat almost instantaneously, as if the liquid had become a perfect highway for heat. No resistance, no delay. The Leiden team had no framework to explain this. Then, viscosity. As helium cooled toward the lambda point, its resistance to flow, its stickiness began dropping. Normal liquids get thicker when cold. But helium was doing the opposite, getting thinner, more fluid, freer. Below the lambda point, it seemed to have almost no viscosity at all. Technicians started noticing liquid levels in sealed containers dropping unexpectedly. Helium was escaping through walls that should have been impenetrable. The joints of the containers were tested and found to be perfectly sealed. No leaks. Yet the helium kept disappearing. Nobody could account for it. The evaporation rates were also wrong. Helium was evaporating faster than the thermodynamics said it should, as if something was actively pulling heat into the liquid. The liquid seemed to be reaching out to its surroundings, hungry for energy from anywhere it could find it. Walls, air, the container itself. The Leiden researchers kept meticulous records. Every anomaly logged, every strange reading noted. The data piled up, but no explanation arrived. They were watching something entirely new, not a flaw in their instruments, not a mistake in procedure. The liquid itself was the problem, and the mystery. The mystery had been sitting in laboratories for years. Liquid helium was doing things that made no sense, and nobody had a clean answer. But in 1937, Pyotr Kapitsa in Moscow decided he was going to get a definitive answer. Not a hint, not an anomaly, a number. His experiment was elegant in its simplicity. He would force liquid helium through an impossibly thin gap and measure how much it resisted. Any normal liquid forced through a tiny gap slows down. Friction fights it. Viscosity is the measure of that fight. More viscous means more resistance. Water flows freely. Honey barely moves. It's internal friction, molecule against molecule. Kapitsa's gap was so thin that even tiny amounts of viscosity would bring the flow to a near standstill. The setup was exquisitely sensitive. He chilled the helium below the lambda point, that strange transition at 2.17 Kelvin, and then he watched the flow rate. It didn't slow. It didn't resist. It poured through the gap as if the gap wasn't even there. The flow rate was enormous. He ran the calculation. The viscosity of helium-2 below the lambda point wasn't just low. It was, within measurement precision, zero. Not nearly zero. Not practically zero for engineering purposes. Zero. Absolute absence of internal friction. At almost exactly the same moment, 5,000 kilometers away in Cambridge, John Allen and Don Missener were getting the same impossible result. 2 labs, 2 continents, 2 independent experiments, both measuring something that physics had never seen before. Kapitsa moved fast. He wrote up his results and submitted them to Nature in December 1937. His paper landed first. And in that paper, Kapitsa gave it a name. He called it superfluidity. the word that would define an entirely new state of matter. Zero viscosity isn't just a curiosity. It means nothing. No container wall, no gravity, no obstacle can create friction to stop the flow. That's why it climbs. That's why nothing stops it. With zero viscosity, the superfluid doesn't just flow, it cannot be contained. It was 1937, and Pyotr Kapitsa in Moscow had a question gnawing at him. What exactly makes helium below the lambda point so impossibly strange? He designed a precise experiment to measure viscosity directly, and the answer he got was not small. It was zero. Absolute zero. No friction. None. Zero. Not nearly zero. Not vanishingly small. Absolute zero viscosity. Kapitsa stared at his own data and could barely believe what he was reading. A liquid with no viscosity means nothing resists its flow. Nothing slows it down. It moves as if friction simply does not exist in its universe. Normal liquids cling. They resist. Even water, poured thin enough, slows and stops. Superfluid helium does not. It keeps going forever. But zero viscosity was only the beginning. Because when you remove friction, something extraordinary becomes possible. Something that should be physically impossible. The liquid starts to climb, up the inside wall of its container, over the rim, and down the outside, against gravity, by itself. This is the Rollin film, named after Bernard Rollin, who first carefully documented it. A layer so thin it is only atoms thick, yet it moves with purpose. What drives it? Van der Waals forces the same weak attraction that makes molecules stick faintly to surfaces. But without viscosity to resist, even that tiny pull is enough. In any normal liquid, viscosity would fight that pull and win instantly. But superfluid helium has nothing fighting back, so Van der Waals always wins. The film coats every surface it contacts. Glass, metal, it does not matter. Touch superfluid helium with anything, and the film begins its journey immediately. Now, picture a container sitting inside a larger bath of superfluid helium. The film climbs out of the inner vessel, over the rim, and pours into the outer bath. The levels equalize, slowly, silently. The inner container empties itself. Gravity did not win. Quantum physics found another route. And if there is no outer bath, if the container sits alone, the film climbs out anyway, drips off the bottom, and the container empties onto the floor. Lab workers learned this the hard way. They would carefully fill a dewar with liquid helium, walk away, and return to find it completely empty. No spills, no leaks. Gone. There was no crack, no valve left open. The helium had simply climbed out by itself over the walls and evaporated into the air. The container defeated itself. This was the moment quantum mechanics stopped being abstract. It was dripping onto laboratory floors. It was emptying expensive equipment overnight. The quantum world had reached up through the floor of the invisible and grabbed the real. And it was doing it every night, in every lab that dared to cool helium cold enough. Here is what that looks like in practice. A thin, invisible sheet of helium, just a few hundred atoms thick, silently creeps up the inner wall of any container it touches. It goes over the rim, down the outside. Drop by drop, the liquid empties itself, and lab workers return to find their dewars completely drained, the helium simply gone. The helium was simply gone. No spill, no crack, no leak. Just an empty dewar and a puddle on the floor outside it. Scientists were baffled. The fluid had climbed out on its own. Something was deeply, fundamentally wrong with how they understood this liquid. Enter Fritz London, a theoretical physicist who had already shaken up chemistry. Now he turned his full attention to helium. London's radical idea: this isn't a quirky fluid. This is quantum mechanics operating at the scale you can see with your naked eye. Every other liquid you know obeys classical physics. Helium, 4 below the lambda point, does not. It plays by quantum rules, and quantum rules have no mercy. London pointed to a prediction Einstein had made back in 1925. Cool bosons down far enough, and something extraordinary happens. They all pile into the same quantum ground state. Not some of them, all of them. The entire population collapses into one single state of being. This is Bose-Einstein condensation. London proposed helium, 4 below 2.17 Kelvin, was exactly this, the first real-world Bose-Einstein condensate. The whole liquid becomes one coherent quantum object, one wave function, one identity, billions of atoms, acting as a single entity. And a single quantum object has no internal friction. There is nothing to scatter off of, nothing to slow it down. Viscosity becomes zero. That climbing film? It's the quantum ground state, refusing to be confined. It will find every surface, every wall, every route out. London published his theory in 1938. The physics community was stunned. This was not supposed to be possible. Quantum mechanics was supposed to stay microscopic atoms, electrons, tiny invisible things, not a beaker you could hold in your hand. But London had just drawn a straight line from quantum theory to a beaker sitting on a bench. The microscopic and the macroscopic were the same thing. The climbing, the escaping, the zero viscosity, none of it was a quirk. It was quantum mechanics refusing to be contained, at any scale. One man had looked at a puddle on a lab floor and seen the quantum nature of reality. The universe had been hiding in plain sight all along. Fritz London saw what everyone else had missed. This wasn't strange fluid behavior. This was quantum mechanics blown up to the size of a beaker. Below the lambda point, helium atoms stop acting individually. They collapse into a single shared quantum state, one massive wave, moving as one, impossible to slow down. That single quantum wave doesn't just sit there. It acts, it flows without friction. It climbs walls. It refuses every boundary you try to give it. This wasn't just a laboratory curiosity. What Kapitsa found in that Leyden flask was a door, and behind it was half of modern technology. Take MRI machines. Every hospital scanner in the world relies on superconducting magnets cooled by liquid helium to near absolute zero. Without helium holding those coils at 4 Kelvin, the magnets would die, the field would collapse, the image would vanish. Particle accelerators like CERN's Large Hadron Collider use thousands of superconducting magnets, all of them bathed in superfluid helium. They push protons to 99.99999% the speed of light. The only thing keeping the whole system from melting is superfluid helium at 1.9 Kelvin. And quantum computing, the next frontier, needs qubits cooled to millikelvin temperatures. The path runs straight through superfluid physics. And it all traces back to Bose-Einstein condensation, the theory that said, at the right temperature, particles stop being individuals and become one. Fritz London saw at first that superfluidity was Bose-Einstein condensation made real, made visible, made touchable in a glass jar. The physics community didn't fully accept it for years. But time, as it always does, proved the theorist right. And then, in 1978, the call came. Pyotr Kapitsa was awarded the Nobel Prize in Physics 38 years after discovering superfluidity. 38 years, spent under house arrest, cut off from the West, working in a Moscow lab with instruments he built himself. The universe had rewarded patience, and the discovery that earned that medal was as strange as ever, a liquid that climbs uphill and cannot be stopped. We look for quantum mechanics in atom smashers and supercolliders. But it was here all along, in a beaker, on a lab bench, climbing a wall in plain sight. The liquid is still climbing. It always will be. Because quantum mechanics doesn't care whether you're watching, it just keeps going. If this blew your mind, subscribe and watch what happens when we ask, what is the coldest place in the known universe? The answer will surprise you.